kind of a solution for transportation liquid waste. And I think it's obvious that we need some kind of and renewable energy that does not produce CO2 net CO2. And right now, everybody is focusing on ethanol. Some people have been focusing on biodiesel that has been made from vegetable oils. And the problem that we notice here is that all of these compounds are produced from food. And they about 80% of the final product value is because of the and therefore it becomes very difficult to produce them without we are used to having products that cost about rice farmers came to us, they were very interested in making biodiesel. No, and as you know that the rice report here, they don't use any now. So we suggested, okay, you can add 1/4 of the acre, we're not being used, you can have a sustainable system. After all that, then they found out that they can sell food, and therefore they forgot about all the biodiesel. All our efforts in helping, trying to make them a co-op and therefore very sustainably and everything went down the drain. So that's type of issues we need to worry about. Another thing that we need to worry about is the fact is that we consume I think in 2008 we consumed about 60 billion gallons of diesel and 160 billion gallons of gasoline in the United States alone. So we're talking about trying to do that. You can look at ultimately the sunlight and the CO2 from the plant. These are the cheapest sources that are. The problem is that we can use plants, they require land. We can use aquatic plants. They think that everybody says that they can produce in non-arable lands, but still they require a lot of things. Ouch. That's a separate thing. We'll talk only about what we can use using waste materials that are and waste materials are still interesting because there is a significant amount of it is present. At this present time, in 2012, in the time we can do that like now we decided that we are not going to work on that for many people. Many people are working on it. And secondly, it locks us into the direction of going as an additive integration. So we decided that maybe a better idea is to look into liquids. You heard yesterday was a big problem, and it remains a big problem. Okay? So we decided that we are going to be looking at the microbial oil soap. These are the triglycerides, okay, which have the fatty acid chains, okay, and we can convert them into some very useful compounds. Now the good thing about it is the microorganisms also produce within these particular triglycerides, fatty acids. Some of them are very valuable as nutraceuticals. So from a biorefinery perspective, it allows us a possibility of producing some very high value compounds as well, to the extent that they are needed, and therefore improve the total economy. But I'm going to show you some of the economy data today will not account for this fact, because the separations and all that is also going to cost, and we did not have that information at the present time. I want to show you here, and I'm presuming that this biomass can be converted from network and the situation to waiting cost, and of course you do separate solving. You could go ahead and you say either carbon, nitrogen, or phosphate. The phosphate concentration is 20 times, okay, and it still produce as much of liquid extraction. The cost went down from about $7 to about 33 cents. Okay. When it comes down to yeast extract, the first idea was, well, maybe we are also providing too much of the yeast extract. So we can try to find out how much yeast extract we need minimum. It so turned out that yeast extract we just could not produce. Yeah, it was too little. Okay. So we decided to replace it with the essential vitamins that are in methanol and calcium pentactinate. Okay. Using a CCF response surface methodology. Okay. And in this particular case, you could notice that once we have optimized it, okay, it so turned out that happened to be the amounts that are present in 1.5 grams per liter of the yeast extract. Yeah. But the cost of these particular items on a bulk from about $3.60 to about 22 cents per gallon of the lipid that we use. Okay. So one of the things that we need to be very careful about is this: the things that look very cheap when you work it out in the lab, because you are putting very small quantities of it. When you are trying to produce in large quantities, you may notice that the costs balloon very quickly. Okay, so you need to use the cheapest possible material and as little as you can in this particular high density cultivations. Okay, the so-called fed bag cultivation. And we did only so far. We were able to increase the lipid densities from about 5 grams a liter to about 33 grams. And did the aspect simulation again. Okay. And in this particular case, we notice another one. And we all know the economy of scale is very important. You could have very small scale of operation and you have a problem. Okay. In this particular case, if you can get up to about 10 million gallons a year, it's not a very big plant. Okay. As much as we can. Okay. But we do still need to find out the low cost carbon sources. Okay. If we can do that, we might be able to make a significant dent into the requirements of the transportation systems using renewable fuels. And with that, I'll stop and take it.
Questions for the speaker?
Yes.
So we're using white spring or recombinant spring?
No, we are not using any recombinant sugar. We are already producing 75% of this. They are growing very fast. In about 100 hours, we can produce some. Yes, there is an effort going on in the algae strains that will grow. But we are not working on it.
We're good. In the interest of time, we can talk to the speaker afterwards and thank the speaker once again. Are there any representatives from the third paper?
No, that's
So in that regard, I'd ask Dr. Mohammed Farid from the University of Auckland.
Okay. Good morning to you. It's my pleasure to be here. This is my first time in the Punjab, but I have been quite a few times to India. The first visit was, I think, in 1984 to IIT Delhi. And I would like to thank the organizing committee for inviting me to give this speech. At the University of Auckland in New Zealand, we've been working on biofuel and biodiesel and bioethanol both, but I will not talk about subjects. I'll switch on now to another aspect of trying to save energy by using it more efficiently. And the approach in this case is storage. So we have been involved in developing materials which undergo phase transition depending on the application, the melting point, which is the most important thing. This material has to have high latent heat and has to be encapsulated in a way which does not interact with the environment. So we developed our techniques of micro and macro encapsulation, which I don't think I have the time today to talk about, and we have used it in a number of applications. Again, the time will not allow me to talk about all applications. The major application is building for keeping the environment comfortable with minimum and minimize heating and cooling, air conditioning. But we have applied it to other applications like cold store, cooling of electronic devices, production of very efficient battery cooled passively, where there is a company now in Chicago producing battery, lithium-ion battery based on this patient material. One of my students was successful in commercializing one of the ideas. I'll probably be, within the time allowed, I will be probably focusing on building because of the. So, this project is being funded by the Ministry of Innovation in New Zealand for 5 years, and a large group of people with it's only me as a chemical engineer. I had professors and mechanical engineers, civil engineer, architect working with me, and a large number of students over the last on the application. What is phase change material? I'm pretty sure most of you know this aspect that the latent heat of energy storage is very large compared to the sensible heat. And I am trying to address about how do we sort this material and
also by comparing the next we have calculate the thermodynamic parameters, that is Gibbs free energy, change in enthalpy and change in entropy from Langmuir constant. From these parameters, we are sure that negative value of del G confirm the spontaneity and by using acids, base, and also organic solvents. For electrolytic salts, we have studied the effect of electrolytes on the bisorption study. While we compare the effect of electrolyte up to the electrolyte didn't have any effect on the bisorption process up to 0.5%. But even when we increase the electrolyte concentration up to 1.5%, this is just a weight by volume ratio. 1.5. I can dissolve the dye and I can reuse it again. Yes, both dyes and adsorbent.
We usually have it facing north because we are in the southern hemisphere. The energy losses, as you see it, from windows, from the floor, and you can see the solar radiation is quite high. Although the ambient temperature is not very high in the weather of Auckland, but we have quite clear sky, so we have high solar radiation. This is the probably important figure. These measurements are the interior temperature inside the two offices. The purple one is the normal office, and you can see the temperature oscillate between maximum 30 to minimum of 17, between day and night. So, hot during the day, cool at night. The other room, which is identical in everything except it contains the phase change material in the chipboard, is shown by the black line, and you can see the damping effect which has caused by the phase change material. So no air conditioning, nothing. This was run just. I wanted to show you another period of measurement deliberately to show that the phase change material in these days did not work. So you have beautiful effect here, you have great effect here, you have reasonable effect here, you have no effect in this period. And that is because the night temperature did not drop on those few days. However, in most of the summer period, it is effective and it did work. And our prediction within Auckland weather in New Zealand, you can really eliminate completely the use of air conditioning in summer. Now, obviously, we have tested the performance in the city of Auckland, and we were interested to test the performance in a number of countries. And we cannot do that experimentally, so we had to go and do computer simulation and look at different places. In the computer simulation, we have used software developed by architect engineers called Energy Plus, and we had to understand a little bit as a chemical engineer the concepts of that, and succeeded in predicting our measurements between the green and red, as you see, in a reasonable way. There are many parameters, so it's really a little bit hard because you need to simulate the movements of the people, the appliance in your house. And what you see in front of you, this house, two-story house.
This is the time we have to hold questions. If you have questions to the professor, you can ask after the session.
What's the material which you are
Sorry,
using?
we have to wait till after the session in the interest of time. Well, the next speaker come forward, Dr. Krishna from Florida.
मेरी देखो चला रही तो हाल हो जाएगा तो तेरी लेट हो जाएगा
Good morning, everyone. Thanks for inviting me to give a talk in this conference. So I'm sorry for the title change. I don't know how it was built. There's some enzymatic hydrolysis in the program booklet. So what I'll be telling you today is about in the last 3 to 4 years is a totally new project that we started on. Is trying to develop a biorefinery concept for conversion of agricultural residues to biofuels and value-added chemicals. So this is the first 2 years, but in the last year or so, I think significant progress has been made by my graduate student Barry Brodius because he realized he wants to graduate next year. So, and this work is also done in collaboration with my colleagues, John Dallon, who is a professor, and John Collier, who is a professor in the Department of Chemical and Biomedical Engineering. Background, this is a traditional biomass to ethanol schematic. So what happens is first you harvest your biomass, and then you undergo a size reduction. Then after size reduction is a very important step called pretreatment, which accounts for nearly 30 cents per gallon. And what happens in pre-treatment is, you have an acid-based pre-treatment, alkali, you have novel solvents. What happens is you break up the crystalline cellulose, make it more amorphous, make it more accessible to enzymatic attack. I'll tell you a little bit in the next few slides. And once you do that, there's an important detoxification neutralization step. You got to remove the, neutralize the acid, maybe remove it, remove the alkali. And after that, you do a solid liquid separation, get the biomass into a reactor, add enzymes. The enzymes breaks up the cellulose to give you simple sugars, like I say, a one-pot reactor, right? So you do the size reduction, you do pre-treatment, but at the same time, now there is no solid liquid separation step, so the pre-treatment conditions should be such that,
Characterized by high color, low BOD due to biological recalcitrant nature of the dye, high COD, and this results in the stringent pollution control laws, and the treatment cost is also high. So we must think on some cost-effective treatment techniques. So recently, AOTs have been studied to explore the treatment of dyeing effluent by using these technologies. Advanced oxidation processes, they are characterized by the generation and use of hydroxyl-free radicals. So hydroxyl-free radical is the second most strong oxidizing agent after fluorine. So they are highly reactive and non-selective. So this property is particularly useful for treatment of dyeing effluent, because in the dyeing effluent we are having a mixture of dyes. So AOT technologies are broadly classified into two categories: homogeneous photocatalysis and heterogeneous. Homogeneous photocatalysis, we use some oxidizing agents to generate OH-free radicals, and in heterogeneous photocatalysis, greater than the band gap energy of a semiconductor falls on it. So the electron jumps from the valence band to the conduction band, leaving behind the positive holes.
so what a good pre-treatment has to do is to break up this polymer and solid liquid separation step before you can proceed with the hydrolysis and fermentation. So what got us into this work? It was John Collier, who moved from Tennessee to Tallahassee. And he spins a lot of cellulose fibers. He works a lot in the textile industry, and spinning fibers, CMS, what really call it. So when in spinning fibers, commercial solvent is N-methyl morpholine oxide, also commercially called the lyocell solvent. It is commercial, is extensively used in dissolving cellulose and in spinning fibers. And what is shown here is basically a capillary rheometer, where you dissolve cellulose in the solvent, and then you extrude it, and then you rapidly quench it. The classic fiber spinning process. So when he came in, over a cup of coffee, we were discussing so if this solvent is excellent in dissolving cellulose in the spinning fibers, can't we use it for pre-treatment, right? So which means that it is good in dissolving cellulose. It's it is biodegradable, though we didn't understand what that meant. That was what was mentioned on the company website. And so we did find out that biodegradable also means bacteria and other organisms can survive in the presence of solvent, so that is good. So it's a low vapor pressure, which means more than 99% can be recovered, very similar to the ionic liquids. And so we thought was, can we use this solvent for our pre-treatment of biomass, and then try to develop our biorefinery process.
हाँ सर, जहाँ सब साथ में हैं। ठीक है सर, नेक्स्ट। जहाँ सर साथ ही हो जाइए, हाँ, पकड़ लीजिए, हाँ, वेरी गुड।
Okay. So.
एक मिनट बस, एक मिनट। हाँ जी सर, थैंक यू।
Thank you very much. Thank you very much for arranging that. Thank you very much.
Wait. Thank you.
Great, thank you very much. How do we get these photos?
Send them to you?
You mail?
Yeah,
Okay.
use your card.
I'll give you my card.
Yes, sure. We'll give the photograph and the reviews.
That would be great. Okay. All right. Thank you very
It was an
much.
honor to have you there.
Thank you very much.
Projects that we are working on. Okay, so this is another interesting find in our lab as well. This is pretty decent. So what we find is also, this is sugar concentration as a function of time during enzymatic hydrolysis of NMMO treated pulp. So when we don't have any NMMO, we get almost up to 100% conversion. So the NMMO, there's not much of a dip in the final sugar yield after like 72 hours. So there's also a little bit encouraging in the sense that hydrolysis. So that is an interesting thing that we saw. So we did start working with solvent. Actually found out that 90 degrees C with 1 hour gives you good results, and this is the composition of the untreated and the NMMO treated barriers. And as you can see, actually NMMO is a very highly basic solvent in its monohydrate form, which is what you have to use. The pH is pretty high, so we think it dissolves lignin as well. So, as you can see, there's not much of a composition change upon.
Thank you, sir.
This is now going to hold questions. You can find the speaker after the session. Srivastava from VARC.
So we have the inside, so that way we go back on schedule and we can hopefully finish on time.
But on the other hand, parties is not allowed to ask any question. I do not think it's a good concept. No, I know, but then we should conclude.
Okay, so you can just settle for a moment, let our speaker begin his presentation.
Good morning to all of you. This is me only, so I am not prepared for somebody else to speak on behalf of somebody. So yesterday you have heard about the energy scenario and contribution of nuclear energy from our Department of Energy. Dr. Banerjee spoke to you at length, and the 3-phase program he told you in a very, which I hope to, in which way we are trying to contribute to overall energy scenario. But there is another facet of our DA programs as such, which I thought I will share with you, and in that only water I will focus more, not there. Let me share it. For human sustainability as a whole, you require energy, certainly. You require a good environment, yes. You require good food, you require good health, and also a good water drink, in addition to a good security for all of us. So, away from the terrorism. So in these presentations, I'll just try to give you a glimpse